All right, so we're going to record this, and this is 7-2. It's a one-day lesson. We're going to begin with the PowerPoint. I'm going to go through these slides with you. So, right, we got to calculate the center and spread, the sampling distribution of the sample proportion p hat. Determine if it's approximately normal, and then we could use the normal distribution to calculate probabilities involving p hat. So the issue is all of this section, 7.2 is proportions. All of 7.3 is means. And then here we have this picture, and these are all sample proportions. All these p hats are stacked, okay? So this is saying 50 samples, they're all the same size. And that's what proportion you got. It's the picture more than the context of the question. Now, these pictures are helpful, okay? If I'm looking at this, sampling distribution of p hat, and you look at the first column, and what happened? The proportion of success is 10% in the first column, it's 50% in the second column, and it's 90% in the third column. But in the first row, the sample size is 25, and in the second row, the sample size is 100. So the first row is not going to meet the conditions. That make sense? If you multiply the proportion, 10% times 25 is just 2.5. It's less than 10. 50%. Ends 25, that meets it, ready? 90% times 25 meets it, but 10% doesn't. So in these pictures, the middle picture in the first row and the whole bottom row meet the conditions, and you can look at the shapes of the graph. Talk about skewness here, which we're familiar with. The mean of the sampling distribution, p hat, is equal to the population parameter. So the step depends upon N and P. And we'll get through it. Don't worry about this. We'll go through a specific example of that. And then why this is true. The step's going to get smaller as the sample size gets larger. So you got to be able to read this, ready? The mean of the sampling distribution of p hat is mu sub p hat. Mu, the center of sub p hat. It's the center of the sampling distribution, which goes to the parameter. Here's the algorithm, which is a new formula for the step, which we'll go over. We're referring to the 10% condition there. The 10% condition is saying your sample's not too big, and then it's going to be approximately normal if n times p and n times 1 takeaway p are both at least 10. All right. So Here is the formula you just saw. On your formula sheet, it's right here. It's sigma sub p hat, which is a new one, except we're going to help you see where it's going to make this much clearer to you when we get to the PDF. All right. And then this is for 7.3, right underneath it. It's saying mu of x bar. Here is mu of p hat, the step for p hat. Here is the center for a mean. Here is the step for a mean. These two algorithms are for what you're doing in 7.2, and these two are for what we're going to get to in 7.3. So the mean of the sampling distribution, mu of p equals p. The standard deviation, well, there's that algorithm you saw. Where's it coming from? We go back to what we did in 6.3 for a binomial distribution. And what was the step? That was n, the square root of n times p times 1 take away p. And what are we doing? We're doing a size change of this of magnitude 1 over n because we're going to a proportion. So doing a size change of 1 over n to this algorithm is the same thing as 1 over the square root of n squared. Because I can distribute fractional exponent over division. So when I take this and divide it by the square root of n squared, it would all be under one root sign. And what would happen? One of the n's in the denominator would reduce with this n in the numerator and leave you with the new algorithm. So even though it seems like we're piling on here and you have something else you're accountable for, the issue is all you did is take what we did in chapter 6 for a binomial distribution and just divided it by the sample size. But because it was under a root sign, we divided it by the square root of n squared. See, if you look at this thing and you're not clear on what's going on, it looks like they took this n and slid it from here to the denominator. Well, it appears that way, but really what they did was divide by the square root of n squared. Okay, and then there's the conditions. So they talked about this. The spread depends upon n and the proportion. And if you don't know, ready, the safest value to put in there, if I'm multiplying by this, we have, in this case, n's 1. We have 1 times x times 1 take away x. So if we don't know p, we don't know what the proportion is, in order to have the safest margin of error for the spread, we would use 0.5. And you see here 0.5 gives you the highest output under these circumstances. So this would be, depends on n and p, the n in this graphic is understood to be 1. And it's 1, square root of 1 times p times 1 take away p. If we don't know p, we use 0.5. Okay? So we're just going to pause this and send you to do 2 questions, 35 and 37. And we'll come back and go over those. Sorry, I'm going to start over again because I forgot to record it. So, question A asks, identify the mean of the sampling distribution. So the mean of the sampling distribution is going to match the parameter. So that's the 20%. The step would be success, orange Skittles, times failure, not orange Skittles, divided by the sample size. That's the variance. You take the square root of that, and that's your standard deviation for the sampling distribution of orange Skittles. So what is it? How do you interpret that? In a simple random sample of size 30, the proportion of orange Skittles will typically vary from 20% by about 7%. So between 13 and 27%. Is this thing approximately normal? Well, it doesn't meet the condition because n times p, the sample size times proportion of success, is less than 10. it's not met, you cannot consider the sample distribution would not be normally distributed. Okay. And then 37 asks, what sample size would be required to reduce the step to 1/2? So instead of 7%, we want the step to be 3.5%. This is just an algebra problem. So here's the answer we got. We did 35. We want this to be half of 7.5%. So what are we doing? To multiply this by 1/2, and it's under the root sign, we would multiply the square root of 1/4. Because 1/2 is equal, ready? If I wanted to put that under a root sign, then I take the square root of the numerator. Square root of 1 is 1, the square root of 4 is 2. So I can rewrite the square root of 1/4 is another way of writing 1/2. If I distribute that over here, the numerator stays the same. Under the root sign, you would have, this is essentially root 30 in the denominator times root 4, and your denominator would be 120. So expanding the sample size by a factor of 4 would cut the step in half. Okay? And you can just, you just look at this algebra and doesn't have to be cut in half. It could be any magnitude just by doing this, this work here. All right, so that's it for 7.